So now that we've known how a basis rule work, we can sort of try and learn a Bayesian network. So Bayesian network itself, see, I mentioned about the operations is fully based on basis rule, and the graphical side of things is actually directly a cyclic graph. And so Bayesian network in the field of causal inference, really importantly, is about the marrying between this graphical structure as well as the statistic operations. So to learn a Bayesian network, we need two steps. One is structured learning, meaning that for any given data, we want to try and recover a graph, directly a cyclic graph, basically. And then parameter learning will be that, now that we have the graph and the data, we want to sort of infer the likelihood of the parameters that we have about the model. And so structured learning is all about how to design the arcs. And in many ways, we can sort of incorporate like physical knowledge or expert knowledge into the system, and you manually generate the causal influence between each given variables that you have in the process. Or you can just let automatic structured learning algorithms to repeatedly do conditional independence tests, like I mentioned earlier before in the 3 atomic structure of Bayesian network. So these automatic structured learning algorithms assumed these properties of statistical independence will inform graphical independence. And it sort of like just take whatever 3 variables and do conditional independency test to then therefore recover the structure. Sometimes this wouldn't necessarily work as we expected, and there will be situations where the causal sort of structure just wouldn't be able to be recovered. And so it is always more sort of recommended to use the knowledge-driven network. But it is also dependent on what kind of information you want to denote. So let's say if information flow is all you need, it doesn't necessarily need to be a causal dependency between any 2 given variable. However, in a situation where you want to look at interventions, a causal dependency will be a necessary step to recover. So there are also some other different algorithms that initiate basically score and search. And so this is a little bit of different approach of using statistical independence informing graphical independence. In these type of algorithms, the score and search ones, it basically generate different type of structures and give it an overall score. And then the sampling process basically generate a proposal saying that like, okay, let's propose to change the direction of this arc in reverse, and then we compute a score of a network score, and then compare it to the original threshold and decide whether or not to accept or reject this sort of proposal. And so this score and search algorithms, the common ones are the hill climbing and the taboo search algorithms. And in some of the previous work we've done, we run through different levels of automated structured learning algorithms and try to test out which ones are more robust. And in many ways, the way to judge which of these algorithms works better is to look at how well they can recover the structure of the collider atomic structure out of the 3. So yeah, that's about structured learning. And then parameter learning is all about learning how to fill the conditional probability tables. So to find the parameter set so the easiest way usually is to try and find a parameter set that basically maximizes the likelihood of the posterior probability. And so you can do it by either trying your best to achieve the maximum likelihood or trying to maximum the posteriori. And this is a common algorithm. It's called expectation maximization algorithms. And with these, you would just use training data to sort of to do an expectation step and a maximization step, and to achieve basically the maximum likelihood. And maximum likelihood effectively allow you to sort of present information in a way that like, okay, we found a maximum likelihood model, and now that will be the model that will be able to represent the best of what we have observed given the data that we have at hand. Okay, so now we have learned Bayesian network. Let's put them into work. So the core benefit of using Bayesian network or a causal machine learning model is generally not the type of questions that can be asked, but how these questions can be answered. And so depending on the, I don't know what's going on, depending on the type of cases you can do, you can engineer your project into a form of a causal discovery type of work, or a causal inference type of work, or a counterfactual reasoning type of work. And in my case, I've sort of experienced all of these three in various levels. So for example, at the causal discovery work, I've done a small project on looking at which sort of variables that we have at hand actually contributed the largest proportion towards a person's liver regeneration capacity. And in our case, using the Bayesian network, we found out that the liver iron concentration after a person's surgery actually contributing the largest towards a person's capacity of regenerating liver volume. And this is many ways can be easily done with linear regression or multivariate regression analysis. And you can actually, in fact, just compute all of these coefficients towards the target node and look at which either one of them has the highest proportion in their coefficient terms. So that's about causal discovery. And then for causal inference, I had an experience where I look at to look at the risk of a person developing HCC if they had an incremental disease burden. Let's say, for example, a person going from a healthy state to become obesity, and then they therefore had a higher blood sugar level, and then had a higher liver inflammation status, and a higher liver fat concentration. And so at this incremental situation, disease burden, I can measure the posterior probability of gaining HCC sort of incrementally and see what is the change. And then the other type of project will be the counterfactual reasoning, and this has been something that I've been working hard on recently. And so in this project, what we wanted to look at is to sort of measure what will have happened if the person is treated incompliant or non-compliant to the disease management guideline. And in my case, I'm looking at a liver cancer situation, and I have a data set where some of the patients are treated according to the guidelines, some of the patients were actually not treated to the guideline. So we have the factual cases, and the counterfactual cases is about building a different world where they would either be treated with different options, or they will have to wait longer, or they will have to have the combination of treated with different options and also wait longer, stuff like that. So this is what some approach that you can do with Bayesian networks, and depending on how you engineer the questions to ask, it requires a lot of setup. So it requires the same thing, basically constructing the Bayesian network and then operate the basis rule and compute the posterior probability of the target node that you're interested in. But all of them actually work on with this underlying process of how we compute the posterior probability distribution. And this is largely to do with the sampling from Bayesian network. So in this slide, I just want to show you how the sampling from Bayesian network work, and it's one form of sampling procedure is called forward sampling. So let's say the first step, we have directly a cyclic graph that you have. The first step is that we draw a uniform distribution randomly from between 0 and 1. And so we have an array of number. And then the second step is to find an order that we want to sort of estimate the probability of the value for A, B, C, and D. And so in the directly acyclic graph, we can either do A, B, C, D or A, C, B, D. To just make it simple, we do A, B, C, D in this practice. And so step 3 is to sort of map the random numbers from the Bayesian network based on the previous step that we had already decided the order to. And then we would determine the value of each node based on the likely probability. So the first value is 0.31, and we're looking at estimating the value of A. And so to estimate the value of A, we look at the first conditional probability table where, let's say, the probability of plus A will be from 0 to 0.8, and it's only from 0.8 to 1, it will be the value of minus A. So in this case, the value of A will be plus A, and then the value of B will be plus B. Value of C we will need to look at the third conditional probability table, where we had already considered the value of plus A and plus B in the first two sampling. The value of C will be plus C, and then D, and then you can sort of like continue to do the same thing until you have a number of samples that you want. But how do we answer the conditional probability queries? So in order to answer the conditional probability queries, we basically just do a simple calculation. So let's say if we want to look at the probability of plus D given our samples, it would simply be we count the value of cases that had plus D and divided by the total number of samples. And in our case, it would be 3 divided by 10. A second thing, simple as well, we'll look at cases that are plus A minus B, and then divided by the number of samples. The next thing as well, joint probability distribution of minus A minus B minus C minus D will be 1 divided by 10. And then the next thing we're looking at will be the conditional probability. So this will be what is the probability of minus C given that the evidence is minus D. So to compute this, we need to sort of get the number of query and the evidence divided by the number of evidence. And so in this case, there are 4 out of the 10 that had minus C minus D as the query and as a joint probability between the query and the evidence divided by whichever are minus D. So in this case, it will be 4 divided by 7. And the last thing, you can also do the same thing, because plus D divided by given minus A minus B will be only existing in these two columns. And there is only one case out of those two are actually having a plus D value. So this is how you calculate conditional probability out of a Bayesian network. So we first step, we're just sampling however many samples that we want to get, and then we answer queries like this. So these two steps are actually sort of done in a single steps in many of the sampling algorithms, but this is just behind the scene of how it works. You will have a sampling step and you will have a computation of the query steps.